Okay, so it's my pleasure to introduce our third speaker for this morning's session, Pavlos Tsatsoulis of the Max Planck Institute in Leipzig, and he's going to talk about synchronization by noise for the stochastic quantization equation in dimension 2 and 3.
Okay, thank you for the introduction, Tom. And let me thank all the organizers for bringing everything together and giving us the opportunity to present our work at another very long meeting, despite the difficult times. You've really done a great job. So today I would like to discuss a joint work with Benjamin Guess on synchronization by noise. Let me just go straight to the point and explain what synchronization by noise means. So we consider a scalar value PD of the following form, where BU is any nonlinearity. And even if solutions to this PD exist, the long-time behavior might be chaotic. Now we can perturb the same equation by some random forcing C, say for example space-time white noise, and it's natural to ask how this perturbation affects the behavior of the long-time dynamics. So we say that synchronization by noise occurs when the random attractor of the SPDE is a siglet norm of Stochastic. And in this case, trajectories of the equation should converge to each other in some sense. Let me give you a very simple example in the finite dimensional case, which comes from a double well potential. So I want to consider the ODE du equal minus C cubed plus U, which has an attractor A given by plus minus 1 and 0. So as we see in the simulation, trajectories that start around 1, they asymptotically become equal to 1. Trajectories that start around minus 1, they asymptotically become equal to minus 1, and 0 stays at 0. Now, if we perturb the same system with a Brownian motion, we see that the attractor collapses to a single random point. And this is clear from the next simulation, where we can see that after a certain time, actually, we cannot distinguish the different trajectories. Okay, so now this simple example falls into the category of random dynamical systems which are order preserving. Here, order preservation means that there is some partial order in the space where you define your random dynamical system, and solutions to the random dynamical system, they preserve this order. And it was already known for many years that order preservation and ergodicity and some other assumptions imply synchronization. In our simple example, what one can actually prove is that any two trajectories converge to each other in probability as t goes to infinity, and the random attractor is a singleton, the law of which is given by the invariant probability measure. Okay, and now it's very natural to ask whether synchronization by noise is immediate for SPDEs perturbed by space-time white noise under some reasonable assumptions, like order preservation or ergodicity. And the first thing that one notices is that if C is space-time white noise, even for a simple nonlinearity, which comes from a double well potential, the SPD will be singular when the dimension is greater or equal than 2. And solutions actually can be obtained only in dimensions 2 and 3 by normalization. But even in this case, U won't be a function, but it will be a Schwarzschild distribution. This already raises some questions about order preservation, what should be the natural choice. On the other hand, it's well known that strong mixing properties hold even in this singular setting. Okay, so now at the same time when Benjamin Guess and myself were thinking about this problem, there was a paper on the archive by Oleg Dubkovsky and Mikhail Soichov, who studied ergodicity and synchronization for order preserving microframe groups by coupling techniques. There were many interesting observations in that paper. One of the most interesting ingredients for us was the following. So if you take any integer p and you define the functional phi p of f to be the signed LP norm, then for any two functions which are ordered, and here ordering is in the pointwise sense, you can bound the LP norm of the difference to the power of p by the increment of the functional phi p. This in particular implies that phi p is non-decreasing. And you also have a nice bound for the increment of the p with respect to the LP norm of the difference. times a constant which will depend on the LP norm of the two functions individually. Okay, and why is this interesting? So this is interesting because now we assume for the moment that our solution U is a function and preserves the pointwise ordering on the space of functions, plus it satisfies some nice LP bounds. Then for ordering initial data, one can prove that the expectation of the norm of the difference of the two trajectories is bounded by the corresponding Wasserstein distance, which leads to the remark that if mixing holds with respect to the Wasserstein distance, then trajectories of ordering initial data converge to each other. So this is already very interesting observation, and it can be used to study synchronization for many examples of SPDs. But as I told you earlier, we're interested in a singular setting where solutions are actually Schwarz distributions and not functions. So we would like to have a similar framework in the case of distributions. And there is a natural way to extend the pointwise ordering of the space of functions to the space of distributions by asking for two distributions to be ordered if and only if the evaluations from non-negative C-infinity functions is ordered. And then one observes that if we define Bezoff spaces in the right way, then we can obtain norms which are really compatible with this partial order. So usually Bezoff spaces are defined through little good palette blocks, but here what we use is semi-groups. In particular, we take a distribution F and we convolve it with a semi-group. We take its LP norm and then we compensate the blow-up as S goes to 0 by integrating against a suitable weight. For the expert, this should give Bezoff minus alpha PT norm. And equivalently, we can just obtain, a new functional phi by just integrating the functional phi p that I introduced earlier. Okay, now with these definitions, it is easy to prove that the same properties hold also in this setting of Schwarz distributions with this generalization of the pointwise partial ordering of functions. And as a corollary, one obtains the following. One obtains that now if our solution U preserves the partial ordering on the space of Schwarz distributions and it satisfies good bounds with respect to this Bezoff norm, and is mixing with respect to the corresponding Wasserstein distance, the trajectories of ordering initial data converge to each other. Now let me focus on the model that we would like to study and apply this framework. That will be the stochastic quantization equation in dimensions 2 and 3. This is the simplest example of a singular SPD that you can imagine, and it's really obtained by, it has a nonlinearity which comes from a double law potential. I do not want to spend time to explain how one solves this equation. I will just directly define the equation as the limit of U epsilon, where U epsilon is a solution of the same equation driven by a noise which is modified, but renormalized. And okay, nowadays it's just a fact that for suitable choice of renormalization constant C epsilon, which actually diverges as epsilon goes to 0, the limit of U exists, and it gives rise to a stochastic semi-flow, which takes values in the Hilbert space of negative exponent. Basically, that would be a Hilbert space with some norm which looks like the norms I introduced earlier. The only difference is that LP is replaced by L infinity and the integral ds over S is replaced by supreme. Okay, and now one can prove that actually U preserves the partial order on the space of Schwarz distributions, as long as, okay, the initial conditions are sufficiently regular to be able to solve the equation. Okay. And now, as I already mentioned earlier, we also know that we have very nice mixing properties for solution to this equation. And in particular, we can prove that the law of any trajectories converges exponentially fast to each other with respect to the total variation norm uniformly in the initial condition. Okay, and Now we're happy because this looks like the framework I was discussing earlier about Schwarz distributions and ordering on the space of Schwarz distributions. And it seems that actually convergence of trajectories of ordering initial data to each other can be obtained. And now the question is how we can prove convergence of trajectories of initial data which are not ordered. And here we use an extra gradient, which is the so-called coming down from infinity property. Okay, this looks like a very nasty statement. Let me tell you just in a few words what it means. So it basically says that if I take any trajectory, then this satisfies a bound which is uniform in the initial condition as long as the time is strictly positive. And why is this helpful? This is helpful because using some compactness arguments, this allows us to construct two extreme trajectories, u plus and u minus, such that any other trajectory falls in between. And because we had uniform mixing in the initial data, we know that the law of these two extreme trajectories, the laws of these two extreme trajectories mix exponentially fast with respect to the vastest time distance. Okay, and now if you think about what I discussed earlier, and based on that, what we've managed to do, we've managed to construct two trajectories which are ordered and they mix. So they should converge to each other. But since any other trajectory falls in between, then the same should hold for if we just consider any arbitrary trajectories with initial conditions which are not ordered. Okay, and finally we can obtain the following theorem, which allows us to prove a uniform synchronization by noise in the initial condition we quantified. In particular, we can prove that trajectories converge to each other with a rate which is related to the rate of exponential mixing, or spectral gap, as many people like to call it. Okay, so here the important thing is that because of this coming down from infinity property and the fact that we managed to construct these two extreme profiles, we can really smuggle inside the expectation supremum over the initial condition, and this is why we call this uniform synchronization by noise. Now the exponent on the norm might look strange. The reason is that when solving the equation, it's more convenient to work with base of infinity spaces, but the framework that I just discussed works better with base of pp spaces, and this minus d over p is exactly the price that we have to pay to pass from one norm to the other by a base of Sobolev-Obedin. And actually, as a consequence, what we can also prove is that the random attractor is given by a singleton, which has the same law as the invariant probability measure of our SPD. And okay, let me summarize. What we managed to prove now is that we've managed to use order preservation and uniform quantified ergodicity plus a coming down from infinity to prove uniform quantified synchronization by noise. But it would be really interesting to investigate in a more general framework how order preservation and quantified ergodicity implied quantified synchronization by noise. For example, if there is no coming down from infinity and I give you two arbitrary initial conditions which are not necessarily ordered, it is unclear how to even construct profiles, say u minus and u plus, which even might depend on the two initial conditions f and g, so that just these two initial conditions fall in between, and then we can somehow claim that at least for these two trajectories we have some convergence to each other. And maybe a more ambitious question is related to synchronization for vector valued SPDs. But even in the non-singular setting, our knowledge on the topic is limited, and one needs to go beyond order preservation. I think I will thank you, stop here, and leave you with Semper.